Cities are key areas for the transition towards a circular economy, but how can we design circular urban systems when multiple stakeholders, infrastructures, and resource flows are involved? My name is Peter Gruber from AE Intec, and in this presentation, I would like to show a possible approach to address this challenge, the Circularity Optimizer project. Circular solutions in cities often depend on connecting industrial and urban systems, for example, through energy, water, or resource flows. However, implementing such industrial-urban symbiosis concepts is challenging. Planning processes like urban system plannings, urban development involve many stakeholders, like from investment, from public or academic stakeholders. And the data for these planning processes is almost always very fragmented. So decision makers lack tools where they can build scenarios and compare them in a transparent way. The Circularity Optimizer project addresses this gap. It is funded within the Tech Export Bilateral Cooperation Program from the Federal Ministry of Austria and the FFG. And is a program between Austria and China, the Jiangsu region in China. The consortium combines expertise in participatory urban planning, like bus architecture, digital modeling from Akarion GmbH, and sustainable technologies from AE Intec. Pilot applications are currently being developed for the regions Weiz and Gleisdorf, where we see the first results in this presentation, and also in the Jiangsu region in China. So what is the Circularity Optimizer? It is a digital decision to support workflow for planning circular urban systems. It starts with exploring the regional context where spatial data and stakeholders are visualized and integrated. Based on this context, scenarios are developed by combining technologies and actors into potential industrial urban symbiosis systems. These scenarios are then analyzed across multiple dimensions, like the ecological impacts, also the social impacts or economic impacts. The tool allows users to compare different scenarios and discuss the results with other stakeholders. Through this process, the Circularity Optimizer supports a transparent dialogue and a consensus-based decision-making for regional development processes. One of the features of the Circularity Optimizer is the Circular Components Catalog, which provides the technological backbone of the tool. Each technology is first documented in a structured technology fact sheet. Here you can see an example of the industrial heat pump technology fact sheet, where all the relevant inputs are represented and all the relevant outputs of the technologies are represented, together with some technical parameters, like which size is the technology or how much area is sealed by the technology. These reference plans are then translated into some sort of scalable technology models, where all parameters are expressed as functions of one single descriptive variable. In the tool itself, users can select technologies from the catalog and define their scale, such as how much treated wastewater is available in the area, or how much energy is used for production in the area. The selected components are then placed in the spatial model, enabling the creation of scenarios with different technology combinations. To demonstrate the methodology, we applied the approach to a pilot case in the region of Gleisdorf, Austria. The starting point is an existing system centered around the wastewater treatment plant and the surrounding urban infrastructure of the region. On the right, you can see the so-called system symbiosis diagram, where current flows of energy, water, or materials are displayed. It also highlights potentials of unused resources or unused energy flows. Based on the manual analysis of this region, we identified several technologies that could improve circularity in the region. These technologies are membrane distillation, which could enable the nutrient recovery from wastewater streams. Also, phosphorus recovery system could extract phosphorus from sludge and produce a fertilizer product out of it. And maybe a biogas combined heat and power plant could convert sludge-derived biogas into electricity and heat. These technologies form the basis for developing improved circularity scenarios in the region. To evaluate the scenarios, we apply an object-based impact assessment approach. Each building, infrastructure element, or company is represented as one object, which is described by a parameter vector. This vector is composed of a standardized parameter list, including energy flows, material streams, emissions, economic indicators, and socio-cultural data. Based on this data set, the ESG cockpit platform automatically calculates sustainability KPIs aligned with international standards such as the GHG protocol or the European Circular Economy Monitoring Plan. Practical focus lies on some sort of circularity indicators, which measure resource recovery rate, the energy self-sufficiency of the region, and the societal value that is generated by the scenario. The results are then aggregated from the individual objects to the systematic boundary scales. This should enable the scenario evaluation. So based on the calculated KPIs, different scenarios can be compared within the circularity optimizer interface. The system aggregates the object level indicators to the broader perspective and visualizes the results in an intuitive scenario comparison dashboard, where you can see the scenarios that are created by different stakeholders in the tool. In the Gleisdorf pilot case, there was the base scenario and one more advanced technological scenario. The technological scenario shows some significant improvement compared to the status quo. The circular output share increases from 0% to nearly 38%, while the electrical self-sufficiency rises from about 1.4% to 26.2%. At the same time, the system reduces emissions by approximately 227 tons of CO2 equivalents per year, while requiring additional investments of around 1.5 million euros in infrastructure and technologies. These results demonstrate how the circularity optimizer supports a transparent evaluation and informed decision-making for circular urban development. In conclusion, the circularity optimizer provides an integrated decision support approach for circular urban planning by linking a participatory scenario development, a structured technology catalog, and automated impact assessment. The Gleisdorf pilot demonstrates how opportunities can be identified and evaluated using consistent KPIs. The methodology is now being further explored in a transfer case in the Jiangsu region in China, as I mentioned before. And we're looking forward to see results in this region as well. But importantly, circular transitions involve many actors with different priorities and perspectives. And without a shared understanding of system impacts, circular transitions could fail. The circularity optimizer aims to provide exactly this shared perspective. So that's the end of my presentation, and I would like to answer some questions if there are any. Thank you.